Hello everyone, I'm Kevin, and along with my teammates Alex and Emily, we are Synbiotech, and we present to you a technology capable of microbial solar syngas production from CO2 and wastewater. To begin, syngas is a versatile feedstock, but the current main source is through fossil fuels, which is energy intensive and produces emissions. Current photoelectrochemical systems need to operate at high voltages, requiring additional, costly energy input. Additionally, wastewater treatment is energy intensive and produces a lot of emissions. So, our technology lowers these energy requirements and costs while avoiding emissions and treating wastewater.
A microbial photoelectrochemical system takes brewery wastewater and sunlight to make syngas. There are three major components: two circuits with bioanodes and a power management system. The air cathode circuit reduces voltage demand through spontaneous oxygen reduction. The photocathode circuit absorbs sunlight energy and meets the voltage demand to produce syngas through CO2 reduction. And the power management circuit allows energy transfer between the two circuits. The bioanodes use a bacteria known as Geobacter sulfurendus, which can create biofilms to conduct electricity, and this electricity can be produced from the reduction of acetate.
Moving on to the technology status, the overall efficiency of the system is about 25% with high selectivity. The cell lifetime is 29 hours, long compared to similar technologies, and the bioanode is self-stable for years. The syngas production, utilizing 160 breweries with over 9,000 available, needs the same syngas output as a coal-based plant. To match its land area, the production only needs a 32 times increase, satisfying one of the largest concerns of renewable technologies. Our levelized cost is $69 per cubic meter, only a couple orders of magnitude higher than current methods. With achievable future improvements, we can match both the land area and the cost of current fossil fuel technologies.
Now onto some of our advantages. Our assembly has a significantly reduced overall voltage, which equals about 80% less energy needed than that of a photoelectrochemical-based APS system. The Faradaic efficiency was found to be 96.6%, indicating high selectivity towards syngas production. The fundamental materials of the device include carbon brusher felt, silicone, nickel, and wastewater, which are cost-effective and more easily available compared with other PEC systems, which employ iridium oxide and ruthenium oxide as catalysts. Our cell can operate for 29 hours, which previous tech could only operate for several hours at a time. There are 9,709 operational breweries in the US. If we added our assembly to 161 similarly sized breweries, we would meet the same syngas production of the only commercially sized coal gasification plant in the US, which is 840 gigajoules per hour. If we added our assembly to all of the operational breweries, we would produce the same amount of syngas as 60 coal gasification plants. The amount of CO2 prevented is approximately 22.1%, which equals 7,150 tons per year. If expanded to all breweries in the US, the total mass of CO2 avoided would be 69.4 megatons per year. Using the 48C tax incentive, we could receive up to 30% back of what is invested into this project, which is equal to about $220 million. Additionally, we could sell our carbon offset in the form of credits, giving us an additional $276,000 per year per brewery. The market size for syngas in 2024 is expected to be 15 petawatt hours per year, with expected growth to 25.9 petawatt hours per year by 2029. Now onto some of the risks. Further investigation on membrane behaviors will be needed. Also, the photocathode efficiency should be increased up to the current state-of-the-art performance, which would be a 500% increase. Proof of concept needs to happen to scale the process to an engineering level by enhancing current density to 30 to 40 milliamps per centimeter squared via the adjustment of PMC parameters and semiconductor and catalyst optimization, which could increase our production by a couple orders of magnitude and reduce our levelized cost to a similar amount. This brings our cost comparable to current syngas production methods. In addition, the stability of photocathodes and membranes for the prolonged operation of MPEC on a large scale needs to be improved.
In conclusion, current syngas production is very energy intensive and uses non-renewable resources. With our technology, we reduce the energy requirements by 80% through renewable feedstocks, decreasing fossil fuel usage and treating wastewater in a scalable, low-cost fashion. Currently, renewable syngas production is a lucrative industry to get into, and once our assembly is finely tuned, it can be implemented to more locations with any industry with high organic wastewater.